Welcome to this explainer, where we're going to completely transform the complex world of combinatorics into simple, structured logic that literally anyone can master. Have you ever looked at a seemingly impossible math problem, a massive computer code, or even just a huge number of daily choices and felt entirely overwhelmed? Well, today, we're going to change that. We're going to break down the exact mathematical rules that let us systematically count basically anything.
All right, let's kick things off with a really simple, everyday scenario to unlock the foundation of how we count everything from our daily outfits to incredibly complex data. So, if you have 3 shirts and 2 pairs of pants, your instinct probably tells you the answer is 6, right? But why? What is the actual underlying mechanism driving that answer? Well, it all comes down to 2 foundational rules.
Section 1. The Rules of Counting. Building your math superpowers.
Our very first superpower is the addition rule, sometimes called the rule of sum. You're going to use this when you have to choose between mutually exclusive options. That just means tasks that absolutely cannot be performed at the same time. Think about walking into a cafe. You just want a single drink, and they offer 3 types of tea and 4 types of coffee. You have 3 plus 4, which equals 7 different ways to choose. The absolutely crucial point to remember here is that when you see or hear the magic word or, like tea or coffee, you just add those mutually exclusive options together.
Okay, so what happens when we swap that keyword out for and? That tells us we need to multiply, because we're now making independent choices one after the other. We call this the multiplication rule, or the rule of product, and it's used when a procedure can be broken down into sequential stages. Going back to your morning wardrobe, you are choosing a shirt and a pair of pants. Because picking a blue shirt doesn't limit your pants options, the stages are completely independent. 3 choices for stage 1 multiplied by 2 choices for stage 2 gives us our 6 possible outfits. This side-by-side comparison brilliantly illustrates the difference. Honestly, if you only remember one thing today, let it be this breakdown. Addition is your go-to tool for disjoint, either-or paths. Multiplication, on the other hand, is your engine for sequential, both-and stages. If you can confidently identify whether a situation requires an or an and, I promise you, you've already won half the battle.
Section 2. Combining your math powers. Leveling up the complexity.
Let's tackle this one. How many 2-digit even numbers have distinct or different digits? Now, this sounds super straightforward, but there is a bit of a trap here. A 2-digit number cannot start with a 0, right? Because of that specific condition, we actually have to split our logic into 2 separate, mutually exclusive paths to solve this cleanly without messing up our count. We can kind of treat this like a choose-your-own-adventure story. Case 1 locks in a 0 for the units digit at the very end. That leaves us exactly 9 choices for the tens place. Simple enough. Case 2 handles any other even number at the end, so a 2, 4, 6, or 8. That gives us 4 choices there, leaving exactly 8 choices for the tens place, ensuring we don't repeat the digit we just used, and we don't start with 0. We just use our multiplication rule within each of those independent paths. And the grand total? Exactly 41 unique 2-digit even numbers. We just applied the multiplication rule within each specific case, and since a number will fall into case 1 or case 2, we busted out our addition superpower to add 9 and 32 together. See how nicely they stack?
Let's escalate our boss battles a bit. Check out this new constraint, sum or all. We need to figure out how many different numbers we can form using the digits 2, 3, 4, and 5, assuming absolutely no digit repeats. Because we can use sum or all of these 4 digits, we literally have to analyze the 1, 2, 3, and 4-digit combinations entirely separately from each other.
Notice how heavily we are relying on that multiplication rule here. We're basically descending our available choices by 1 each time to make sure no digits are repeated. For a 1-digit number, you just have 4 choices. For a 2-digit number, it's 4 choices for the first spot and 3 choices left for the second, giving us 12. For 3 digits, it's 4 times 3 times 2, which is 24. And for all 4 digits, that's 4 times 3 times 2 times 1, which also happens to equal 24.
Finally, we just use our addition superpower to sum up those 4 independent cases, because remember, a number is either 1-digit, or 2-digit, or 3-digit, or 4-digit, and we get a highly satisfying 64 total possible numbers. It's pretty amazing how quickly we can break down a big, intimidating problem just by layering those 2 fundamental rules.
Section 3. Designing flags in code. Scaling up the multiplication rule.
Let's step out of pure math for a second. Imagine you're tasked with designing a new club flag. It has 6 vertical strips, and you have 4 colors available: yellow, green, blue, and red. The only rule you're given is that no 2 adjacent strips can have the exact same color. What's really fascinating here is how the choice for each strip cascades sequentially. You have 4 choices for the very first strip, obviously, but for the second strip, you only have 3 choices because it can't match the first one. And the third strip, it just can't match the second one. It could absolutely be the same color as the first strip again. So strictly 3 choices remain for every single strip after the first one, just to avoid those clashing colors.
Since we are picking a color for strip 1 and strip 2 and strip 3, we multiply those cascading independent choices together. That is 4 times 3 to the 5th power, and you get an incredible 972 distinct flag designs. Over 900 designs just from 4 colors in one simple rule. That is wild.
Now, we can apply this exact same sequential multiplying logic to computer science. Take binary sequences, where a binary word is just a sequence of zeros and ones. Usually, every position has exactly 2 choices. But what if we force some rules on a 10-character sequence? In case A, we force the word to begin with 3 zeros. That means the first 3 positions have exactly 1 choice. They are locked in. The remaining 7 positions still have their standard 2 choices each. In case B, let's say we force the word to end with 2 ones. That locks the back end, leaving the first 8 positions with 2 choices each. Looking at them side by side really drives the point home. Fixing 3 digits up front in case A limits our total combinations to 128, which is just 2 to the power of 7. Meanwhile, fixing only 2 digits in case B leaves us with double that amount, 256, or 2 to the power of 8. The takeaway here? The fewer constraints you have, the exponentially larger your possibilities become.
Section 4. The Ultimate Counting Challenge. The Final Boss.
Okay, take a deep breath and look at this one. How many times is the digit 0 written when listing all integers from 1 to 3,333? Imagine actually trying to count these zeros by hand. You'd absolutely miss a few, for sure. Instead of doing it the hard way, we're going to break this massive problem down logically by isolating specific ranges of numbers and just checking the decimal positions.
By applying our trusty multiplication rule across 3 distinct ranges, so 1 to 999, then the thousands and 2000s, and finally the home stretch up to 3333, we systematically isolate every single zero based on which decimal place it sits in. We just calculate the exact combinations for each specific constraint within those ranges. And because our number must fall into range 1, or range 2, or range 3, we just apply our addition rule to sum those 3 subtotals up, and boom, the digit 0 is written exactly 963 times. What looked like a completely impossible task at first was easily dismantled using the very first 2 rules we learned today. As a quick final mind-bender, we could even use a clever principle of subtraction for advanced algebraic concepts like onto functions. Let's say you have a set of n elements mapping to exactly 2 elements. Finding how many map cleanly to everything seems pretty tough. But instead, we can just take the total possible sequential functions and simply subtract the 2 lazy constant functions where everything just maps to one single output.
This brilliantly distills highly complex set theory into a beautifully simple and memorable equation. By combining our sequential multiplication rule with a little bit of simple subtraction, we completely bypass some incredibly dense math.
So look at what we've done today. We went from counting combinations of shirts and pants to calculating thousands of abstract data points and binary codes. Armed with the absolute superpowers of and or, I challenge you to go out and see the world not as chaos, but as a series of fascinating, completely solvable puzzles. Seriously, if you can decode complex patterns just by knowing when to add and when to multiply, what else in the world around you is just waiting to be counted? Until next time, keep counting and keep exploring.